Hello everybody, thanks for coming. My name is Sergey Kuksenko. I am from Oracle Java Performance team, and my everyday job is to make Java faster. I am working on all areas, starting from class libraries and fetching JIT compiler everywhere. So right now I'd like to share experience with some technique which sometimes may be useful for performance analysis, to finding performance issues, to do everything with that. So let's start. As an Oracle employee, I have to show you this slide. In really, we are presenters from Oracle love this slide because of it means I could lie for you, tell anything, and it doesn't matter. It saved me. Okay. So I'd like to start from some example, and some technical details will be explained later after that example. So imagine we have an application, and we realize that our application is slow. A couple bit. What does it mean that the application performance of our application is slow? In reality, there is only one metric for that: is customer satisfied or not? And this metric takes a Boolean value. It's very difficult to work with Boolean values. That's why we expand this, doing some measurement, etc. Anyway, imagine we have some application. It's slow, and we found a hot method inside our application. For example, this one. Do you know what does this method do? It's a matrix multiplication, straightforward from algebra. Please raise your hand who wrote such kind of code in university, in your college. A lot of them. Okay, and right now please raise your hand who wrote such kind of code after education, in your work. Nobody. That's fine, because of in reality there is a very serious issue when you show performance examples on real code. You show example, you show how to solve the problem, it starts proliferating through network, different people. It became an urban legend, people start repeat that code, but the situation change, hardware change, virtual machine change, that solution still doesn't work. But it continue propagating through the code of other guys. That's why I love such kind of theoretical examples. What's the problem with that code? You know, this method is the hottest method in our application. What's the problem here? The key problem that is cubic complexity. The complexity of that code is 3 loops, and it's not a very, very effective algorithm. What usually we do if we stuck with some well-known algorithm, well-known things, and we have to make it faster. What usually you do for that?
Like we cache things?
We are going to Google first. Okay, and there is a well-known algorithm which operates faster. It looks like 3 and 2.81. It's not a big difference, but let's check it in reality. Let's implement the fastest Russian algorithm for multiplication and compare. Okay, I did it. I measured it as different values for my matrix. N is one line. And here is the time, how many seconds I need for one multiplication. I'm sorry guys, I can't show a chart in this area. Everybody loves charts, but for these numbers they are so different, it won't be visible on a single chart. So like for matrix 8000 by 8000 elements, I need almost an hour to do multiplication in first way. But when I did a Strassen algorithm, I need less than 5 minutes. Okay, got it. Is our optimization done? What do you think? It's classical way. We found a better algorithm and it works. And here is a chart that shows speed up. which we got, and our speedup is 13 times for large matrices. Let's try the other way. Not going to Google, but trying to use something else. Okay, what I do? I collect some basic hardware counters for this matrix multiplication. This is exactly for this size of matrix. And what could I see here? As I told, these details should be explained later. I see that I spent these huge numbers, different events for the whole multiplication. And if I normalize it per one iteration, I mean iteration of the most inner loop, I need that the most inner loop, it required 8 instructions to execute it, because of I need load one element, the second element, multiply up to value finally. And what I see here, I see that inside one iteration of innermost cycle, innermost loop, I do 4 loading data from memory. In that case, they loaded from, particularly from caches. And 2 of them are cache misses. And we know that cache provides fast operation for us, but cache miss may be not good for performance. Okay, I know that the problem may be in cache misses. If half of my memory operations is cache missed, it's a problem. I start another tool, collect another statistic, and pinpoint the exactly place where the problem happens. The problem happens definitely here. And I don't show this on slide, but particularly both cache misses are happened from loading data from B array. Do we have some guys here who deal with GVM internals or something else? Could you guess why we have 2 cache misses here? Okay, it is short quiz. I give a hint. I want to say that we have 4 memory loads. One of memory load is for array A and 3 memory loads for array B. And 2 of them are cache misses. I will explain later, but after presentation, but maybe you will have time to think about that. So, and our cache miss here, why we get here cache misses? Because of the most inner loop is a loop on a k index, and we change that k index. So access to array B is not cache friendly. Cache loves when you access for subsequent memory locations. It's obvious, it's everywhere. This cache friendliness, it's hardware independent, like Java, because each CPU right now has a cache, and every cache is friendly for subsequent access, for sequential access. It doesn't require for us to know the details of hardware. We just have to understand what's happening here. What we could do here, how we could fight against these cache misses.
Swap the B array.
Yeah, exactly. If we interchange these 2 loops, J and K, in that case we'll got sequential access for array B, and nothing wrong will be happen with array A, because of it operates with A and K indexes. And here is the code. Here's the difference, a little bit difference, which may have an influence later. Like here we make a sum of 2 vectors into one local variable S. And we hope, and usually do, the JIT compiler locates this variable on a register. And only that we are doing only one write to memory, final result. Here we can't do that. In that case, we should load data from result and store result on each iteration. We'll check how it influences. Okay, here is results of that optimization. Here is old code, old sequence of loop ijk as it was written originally, and here is modified akg when I interchange. And here is the time, here is multiply, here is Strassen algorithm, and here is straightforward multiplying again. And we could see that the new algorithm is faster than a Strassen algorithm, in spite of the fact that Strassen algorithm has better theoretical complexity. Because of big O doesn't show for us the constant, which is hidden by this big O. And here we improve that constant. And the other benefits which we get here, the Strassen algorithm doesn't work for small matrices. It's a partition algorithm, and at some level it should use some kind of conventional multiplication, or straightforward multiplication, because of it became ineffective. And my experience show for AJK loop ordering, the 128 is the minimal value when Strassen algorithm give performance benefits. Below, it doesn't work. No effect from that. It's obvious. And let's do later. Because of Strassen algorithm doesn't depend on our inner loops, but it needs some basic multiplication inside. It means that we could make a Strassen matrix multiplication over updated sequence. And here's our other numbers in a second. So the finally, here is a chart. It's a matrix. Here for 128 new Strassen doesn't work. It doesn't give any performance benefits. But here is original Strassen. Here is improved our loop sequence, and here is modified Strassen. And finally, we got, for large matrices, we could get in soon up to 45 times performance boost. That's significantly better. Any question about that example, guys? I will continue. And it doesn't relate it to the topic of our presentation, but it's a nice example from other things to talk about performance. Performance improvements is a non-composable thing. If you have function I, function B, you're doing such composition, you got, from functional point of view, you get a combined result. If you have a performance improvement A, a performance improvement B, you combine it, that you could you can get any kind of result. You can get the performance benefits sum A plus B max from A and B. Even it could be worse and etc. Like here. Here is a combination of Strassen and loop interchange approximately the same. But here, two small performance improvements give results very huge performance improvements, which much larger. And a little bit check what will happen later. Here is my counters about instructions and cache misses. What I see is the green color shows where I could see an improvement. And I see that we have spent much less cycles for our matrix multiplication, much less instruction, much less load data, much less cache misses, and more stores to data as predicted. But anyway, even we have storing data to L1 cache, we have less store misses. So it's good, it's a fine optimization. It doesn't create problems for us. And the other issue, not issue, the suspicious thing which I could see from that number is this. I realize that if I normalize all these numbers by amount of iteration, that internal iteration requires only the single assembly instruction. So I need load data from one array, from second array, multiply them, add to the previous value, store. How could I do this with one instruction? The thing that we got a vectorization. Because of we were fighting against cache misses, and we did sequential access to elements of memory, not even matrix, just sequential access to elements of memory. And we know that such kind of optimization is friendly for caches. But also sequential access to memory is friendly for vectorization. And if in first case hotspot can do vectorization code because of it should load different elements from different places, but here we load a bunch amount of elements array by one instruction and multiply it with SSE operation on x86. Okay, that's all about this example, and here I'll show you the general introduction about the things. Of course, this technique which I show, it's not a silver bullet, and I want to show the example where it may be useful or where not. And again, I would like to ask you, if you have a slow application, what is your first step?
Profile it.
Okay. First step, we should get an answer for the 3 questions in a direct order. First of all, we should understand what's our problem, what creates a problem for us. The second step, we should understand where this shit happens, and only after that we should think about how to fix it. So we should start from monitoring, from profiling, the second step, and tuning. It's a general direction. And the other things which are also useful to know from performance methodology is top-down approach. For Java, for native applications, there is no GM levels, usually 3 levels. For Java, we have 4 levels. It doesn't matter. The difference between these levels and on higher levels, the cost of performance issue is much higher. So you shouldn't dig into microarchitecture levels and think about instruction, cosmetics, etc. if you just load in huge amount of data from some hardware drive produced in 1995. Because of you even won't see that performance issue. So we should start from the top. And we did some presentation about that, me and my colleagues, and we created this mind map, how to dig into some particular areas in some case. But it's impossible to fit it onto slides. That I'll show you a link where you could find and read it. Okay, what we are doing? We start a system monitoring. We start top-down approach. We check what happened in the system. We understand that we got a small amount of system time. If we have a lot of system time, it's a topic of another presentation. We check interruption on other problems. We check input-output. We check idle time. And finally, got it. The only place when we should start to think about our hardware counters is a situation when we reached a high CPU utilization. Before that is a problem on other levels. You just don't need that tools and that technique. And if we reach the high CPU utilization in the place where it could be useful. And the key question, what does 100 CPU utilization means?
High temperature.
What?
High temperature.
No. Okay, I say it's a consequence of that, but what it means if you have 100 or near 100% CPU utilization?
All your cores are busy doing something? Or
Yes, you just have enough something to do. You don't know, is it something useful, is it effective? No, you just have enough task to do. And could traditional profiling help in that situation? Usually, no. Because of profilers show where the problem exists, but not why. Of course, if you execute profiler, you find where you can look into the problem where, and you can guess about problems. Very frequently it works, but sometimes not. And that is why I suggest to use normal order: why, where, how. So what's the reason of this 100 CPU% utilization? The reason of that, their difference. We have just a lot of instruction, a lot of things to do, and load our cores completely. Maybe we have a memory-intensive application and we are sitting in our CPU is just waiting, loading data from memory, pulling data to memory, etc. But in that case, you also will be see 100% CPU utilization. There maybe you have some tricky algorithm which has a lot of branches, a lot of conditions inside, and you constantly stuck with pipeline flashes after branch misprediction. You will see on the top level, you will see 100% utilization, and you won't know details about what happens, etc., etc. A lot of things inside CPU, when executing instruction, your CPU is stalled, outside is shown as 100% CPU load. That is why definitely we need hardware counters to understand why our CPU is stalled or not. Okay, just the hardware counters is quite a simple thing. It's internal hardware profiler inside CPU. Every CPU, I don't know about embedded area, unfortunately, but every CPU nowadays has hardware counters. The first appearance of hardware counters in production CPUs, it was a Pentium, the first Pentium. They had 2 events probably. I don't remember exactly, but it was so successful that it started developing, evaluated later. And you should care about a lot of counters. The first thing, these counters just collect events for us. And events is that area which we should know. Which events we want to collect and which each event should take care for our applications. How to understand which events we need, like we could read Intel documentation. It's intentionally unreadable because of its really awful stuff. I can't explain a lot of events here. I just show you that without reading documentation or reading documentation for particular tools, when these 100 events are listed to explain, you should do that. Anyway, it's required, unfortunately. So which problems exist in that area? A lot of different events. You should understand how microarchitecture works, how CPU done inside, because of it's important for that area, as I told you. It differs, like even inside the one line of CPU, the events may be changed because of hardware vendors are free to do whatever they want here. And okay, how to work with that? Usually it's intentionally designed that counters works in 2 modes. Counting mode, just to execute our application, count events, and got the results of end of application, or selected, or during the selected period of time. It's a counting mode. But what's the most interesting thing is that all counters could be executed in a sampling mode. And if we reach some threshold, we raise interrupt, and in that case, the tool which collect counters for you could find a place where these overflows, this interruption happens, and point you the places where event happened. That is why we could use there are profilers not only showing you where applications spend in time, but show you which issues exist in different places. And there are some issues working with counters. Just list them like we have a lot of events. It's really 100 events for modern CPUs, but the amount of hardware counters is quite small. For latest, not latest already, for modern Intel CPUs are approximately 4 hardware counters. 3 fixed, which can be changed, and 4 counters which collect different events. It creates a problem for our experiments because of either we should execute our application several times to collect different counters and we need repeatability, or there is another situation. Some tools, unfortunately not all of them, but some tools could do multiplexing for you. I told you I could set up for a tool I need for execution for 30 seconds and I won't collect these 30 counters. And that tool will change counters for small periods of time. during the same run. But in that case, you should guarantee that the behavior of your application is the same for a long period of time. We call it steady state. And I'll miss that. I'll tell you that sometimes it's hard to bind, to work with instruction and counters, but it's okay. It's some natural things from hardware. And you could realize that if, for example, tools show you that you have a cache miss on a multiplication instruction, it's not. It should be some load before that multiplication, because of sometimes hardware could pinpoint exactly that place. So typical usages of hardware counters by design, it was two usages. First of all, it's hardware validation and performance analysis, because of hardware vendors loves do performance analysis of application and doing them fast. But in reality, in several years after that, a lot of other different usages appears in the world. There are a lot of them, like runtime tuning. JRocket did it. Who knows about JRocket?
Is it GFR?
No.
Mission control?
No. Mission control is profiler. I mean, it's runtime tuning. JRocket collected a hardware counter statistic, not a profile, which is doing bad hotspot with it's setting different things about code. But it collects counters about application behavior and re-optimize code into new conditions. Unfortunately, it brings some benefits, but not so much benefits of conditional profiling during hotspot compilations. That is why it's not used in hotspot. For me, it was very interesting to read a lot of articles about security and defense areas. Like, I saw a lot of situations when guys collect some hardware counters like branch misprediction or cache misses about the application which is doing encryption, and they significantly reduce brute force space for attack. That is why you can't get access to hardware counters directly. You need to get super user privileges in any operating system, because of it's a problem. But I realized that other guys did some security defenses use hardware counters. If you have a long-running application like a server, it usually operates in the same way. You collect hardware counters, a lot of different hardware counters, and making like snapshot about application behavior. And if this behavior is changed, it may signaling about injection and all other things. About tools. On this page, I show 3 tools which I am using in my performance analysis. First of all, of course, it's Oracle Solaris Studio Performance Analyzer. Don't afraid the word Solaris. It perfectly works on Linux. And it's free. It's a perfect, well-tuned profiler which could profile you in a traditional way, in a time. And also, performance analyzer could collect you different kind of hardware counters and show you places of code where the counter is located. And the second thing, the Solaris Studio Performance Analyzer perfectly works with Java. Like some different tools don't work with Java or badly work with Java. It's quite powerful, cool things. The other tool which I use in my everyday life, it's called perf. Linux guys should know. It's some tool embedded into Linux kernel and help you quickly collect different hardware counters. They choose a bad name because by perf you can't Google anything. That is why their help page and their documentation called perf_events. Try to Google by this. And of course, I have to use our Java micro-benchmark harness. It's a harness which we created for writing micro-benchmarks for Java, which we use in our ordinary life. To it doesn't create benchmarks for you, it just solves routine problems for writing micro benchmarks. And it has some intersection with GMH. GMH could just ask perf to collect different hardware counters, but it could normalize their operations that sometimes may be useful, or even it could show you assembly with the most expensive instruction. Of course, there are other tools, like, first of all, it's tools from vendors. It's AMD, CodeXL, it's Intel VTune. I heard something about all profile, probably it died already. A lot of tools exist. I don't use it, so I can't say anything about that. I used VTune 10 years ago, but I'm not using it right now. I heard rumors that it's significantly changed. They did something very great to show you details about your application behavior, but it's not free. You should pay for Intel for that, not only for CPU, but for this tool. And here is example, and no, there is no common understanding about how to code these events for these tools. Because in Intel documentation we have one names, in perf events we have the other names, in Oracle Studio Performance Analysis we have the different names. But it's okay if you have 2 or 3 tools for your ordinary life, and you used to that. But the key events here, it's amount of cycles and instruction. Okay, I have few amount of time, and a little bit later I'll show a couple another example. But what we have to do with hardware counters, we collected a lot of events. What we have to do, how to understand what doing that. I'm just want to say that our goal for performance improvements is a reduce amount of cycles. Of course, the customer may be satisfied if you bring a bottle of liquid nitrogen and speed up frequency of your CPU, but it's not our way, it's not software optimization. Our goal is reduce amount of cycles which you spend for execution. And usually, if you collect statistics, we should about application, there is such equation like general amount of cycles is a path length, just amount of instruction which you need for some operation, multiplied by CPI, the average number of cycles spent for one instruction. Some guys use other metrics, IPC, but it's almost the same, but in different order. And what we have to do, our goal to reduce amount of cycles, so we have to reduce these result of that multiplication. Our optimization should reduce path length or should reduce CPI, or maybe it's better to reduce both of them. But anyway, sometimes I'm reducing CPI but increasing path length after optimization, but it's okay if the result of multiplication still low. And what does it mean? If you have path length is a metric of your algorithmic efficiency. It's just a simple the number of instructions which you have to execute to do a desired task. It may be, first of all, from hardware counters, it's an assembly instruction, but it's correlated with the amount of Java instruction or Scala instruction you wrote. Just a concept. And CPI is a number of metric which show us CPU efficiency. And here's the typical values for modern architecture. If I see that CPI is 4, it's a problem. So we have a stalls and we should solve that. If I see that CPI is 0.4, I won't care about any kind of stalls. I would look into path length and check if I could do something with path length to reduce amount of instruction for my task. It's a goal of my activity. So if I already got a low CPI, I just tune algorithm and reduce amount of instruction. But if I've got a high CPI, I should find the reason of stall. It could be memory stall, branch stalls, and etc. There are different areas where these stalls appears, but the most frequently appeared problem is a memory bound issue. There are different issues here, and all of them have descriptions and particular counters how collect. The second problem is to be core bound, and we have everything fine as memory, but we're doing some expensive computation inside our core. Front-end bound, at least the least found problems in real applications. Usually we can't do anything here, we just talk with that problem if you talk with such issues like instruction cache misses, but it's already our job. Like in Java 9 we implemented segmented code cache, which significantly reduce instruction cache misses for end-order application. Okay, that's all what I want to tell about hardware counters, because of just shows that guys there is such things. You could dig into that. I just want to show a couple other examples if I hope we'll have time for that. Okay, I'll take the large, standard, well-known for all Java performance guys benchmark. It doesn't matter which, it's particular. I take it. I took it, and I collect hardware counter. Just monitor. Could you see the problem? It's impossible, too much numbers. I drop out everything which is bad, which is irrelevant, and try to make such a table from here. What we have? We have CPI 1.85. It's probably it's bad, but what doing later? How to understand where is the problem here? What I see? My first step, I have a lot of cache load here, first level cache, last level cache here. Maybe cache and memory loading data from memory could be a problem. Let's check. Potential issues. I know that the cost of load data from L1 is 4 cycles. To load data from on that particular machine. Not in general, but I did experiments on particular machine. I know that load data from L2 is cost 12 cycles, and load data from L3 cost 36 cycles. This is load, a pure load. So I need this amount of cycles for loading data from L1. This amount of data to load data from L3. I didn't get L2 statistic here at the first execution. It doesn't include in the list of default counters. I should, but I could guess that if I don't hit into L1, but if I have L1 miss but L3 hits, this value below the difference I hit in L2. It's optimistic assumption because of some of these reads could pass through L2. I don't have last level cache misses here, but it's okay. It's low boundaries. What I got a result. For these all data loads only from caches, even not from memory, I need more cycles than I ever spent of my program execution. How is that possible?
Parallelism?
Which kind of parallelism?
You have multiple cores there on your bars?
No. I have to return here. Nobody's noticed that thing. We have the ideal CPI cycles per instruction is 0.2. But the cycle is a clock tick inside CPU. Nothing in hardware can be done less than in 1 clock. It's a physical limitation of hardware. How we can read some less than 1 cycles per 1 instruction for execution? So because of our CPUs are superscalar architectures and execute a lot of instruction on fly, and it's an average value. So here is the same situation. These loads from caches, we have a lot of them, but they're interleaved. They intersect. That's why in reality we don't know how much time it's required. We could make an assumption that it's memory intensive application, that maybe it's a problem, but without further analysis to trying to locate the exact places, we can't understand where the issue is. It's a superscalar architecture. Okay, the problem is here. I show that example because of if you have a memory intensive application, you should look exactly into TLB. It's the first thing which you have to solve with a memory-intensive application. Who knows what TLB is? Okay, it's a TLB. It's a small but very fast cache inside CPU, which help us when we need a translation from virtual address to physical address. And we need that translation for each memory access, for each memory load and each memory store. That is why it should be very fast cache. And that is why, because of its hardware limitation, it's fast cache, it's small cache. And if our value doesn't hit into that cache, it costs us a lot of performance. And happily, we have different events, at least on Intel hardware, which help us to understand what the problems. This is called event which show us which misses cause the work. Page work is the most expensive things. And even there is another event which count for us the amount of those works. We just could get a statistics how much time we spent on these page works. I collected that, and I realized that work duration is 13% of time. For that particular benchmark, on that particular machine, on that particular execution, I spent 13% of time doing nothing. My execution of my instructions stopped, and waiting until CPU asks operating system, show me the address of my page mapping, how to map virtual address to physical, and after that I will do the load of this byte. We could cause this for even particular separate byte. How to solve TLB problems? There are usually two ways. As I told, every counter works not only in statistic and sampling mode, in counter mode when we collect all data and check what's happening, but you can understand where it happened. And of course, you can find a place where it happened. You could change that data load. In general, it's a suggestion to reduce working set. It doesn't mean, of course, it's ideal if your application could consume less memory, but just splitting in time consume not less memory and overall execution, but less memory at particular point of time will help you. It's the first way, and the second way, just do nothing and turn on large pages. There are a lot of articles how to enable large pages for Java and how to work with that. It's that options. I did it for my benchmark. I did nothing. I didn't change the code. I don't have the code for that benchmark. I just changed the command line option, and I got 20% performance boost. Okay, and a little bit showing the difference which I got the results. I collected statistics for a fixed period of time. That is why the amount of cycles is the same. The CPI is better. The instruction we could execute is better. Even loading data is better, but significantly less TLB misses and time spent on TLB. And the same values, but normalized per transaction. Like we have the same amount of instruction here, but in that case, different amount of cases. And to show what's the difference in that case and how it costs. Okay. Do you have any questions about this? Yeah?
So why it's not a default huge pages?
Because of its default where it's possible. Huge pages are default on Solaris. But on Linux or Windows, you need to do some super user settings for your operating system. That is why it can't be done by default. The other options, at least for Linux, is the options which called transparent huge pages. In case of transparent huge pages, you even don't need to set up this command line option. Because of, in that case, it is transparent, the huge pages provided by operating system for you. But there is some caveats here. Transparent huge pages may be inefficient in some cases. I could explain later way if you wish.
Okay. Sorry, excuse me. When it comes to transparent huge pages, they are known to cause some GC issues, right?
What?
Transparent huge pages, they are known to cause some GC issues when collecting, right?
No.
With the compaction, memory and stuff, right?
You mean, of course, operating system has a GC for pages, and it's a problem not Java, not for Java GC, but for operating system when we collect small pages into large pages. Sometimes when we have large pages, they are not pageable, they're not swapped to hardware disk, and if you want to do paging of our memory, we need split large pages to small pages. So in some scenarios, it creates a performance issue. Sometimes no, you have to check. It's a large topic. And just, I don't know, we have only 5 minutes. Do you prefer third examples or continue questions? It's last example. Okay, let's do example. Who knows what fault sharing is? I realized that the last couple of years there were a lot of discussion about fault sharing. That is why I took that example. What is fault sharing? If you have two variables located somewhere in memory, one near each other, with a high probability they will be located inside one cache line. And I have to say that from a memory point of view, there is no such thing as a byte, and even 4 bytes. It's a virtual entity. Because of bytes for you, it's provided by cache when you split. But from memory point of view, there is one single undivided entity. It's called cache line. And all access to memory is performed by cache lines. The cutting these cache lines per bytes, it's a question near the CPU, not from memory. And if these two elements, two variables are located in the same cache lines, and you have two threads which are doing modification of these variables from different cores, you're in trouble. Because of cache for this core and cache for this core, they have implement consistency of that cache line. But cache line is atomic entity in that place. And it starts to run from one cache to another cache, waiting until data arrives, and then it creates a performance issue. A lot of suggestions how to fix it, etc., etc. Even we did for Java 8 this annotation. It's annotation contained implemented by JEP 142. It's not public, unfortunately. It's for our internal use. There is an option which enables you to use it. As I'm saying, because we really need such kind of annotation to do proper protection of fault sharing for very sensitive place in concurrent utilities, in Java util concurrent package, and etc. This annotation checks the existing hardware and just moves these fields inside one class with some gap. Because of course, there is a way to do it with padding and sort some variables between, but it's not guaranteed that they were not eliminated by hotspot compilation. And just here is the code. We have two fields. Here is we are doing increment from one thread, and we are doing increment for other thread. And here is the results. And our results, they depend on where our two threads executed. So in case of Intel, they could execute it on different cores, or on the same core, which usually has a hyperthreading, on two hyperthreads on the same core, or even on different sockets. And in that cases, you'll have different numbers. It's amount of nanosecond per one increment, in average. So shared case, it's a case where we have fault sharing, and padded, and when we don't have a fault sharing issue. And for example, in case of different circuits, it costs very much. And on that table, I just show which level, which resources shared between these threads. Like on cores, on different cores, we should communicate through L3 cache. In case of hyperthreading, we communicate through L1. And in case of different cores, we don't have any kind of shared cache. It's a problem. And here is hardware counters. Could you find a problem? Yeah, really, guys, neither do I. Neither do I. I just want to say that what's the fault sharing here in case of hyperthread? Our data in L1 cache, where is the fault sharing? The problem is that, as it's called, if you execute two threads on the same core under hyperthreading, there is no such thing as true fault sharing, there is a false fault sharing. In different score we have true fault sharing where our cache line running from one cache to another, but here we got a completely different issue. And probably somewhere in the future this issue will be solved, but the issue is called memory ordering, or there is some piece of hardware which is called disambiguator, track writing from different hyperthreads in the same hardware and trying to understand is there a conflict or not. If this disambiguator tells the CPU that there is no address conflicts for writing and reading from memory, this operation could be executed in parallel. If there is a conflict, it stop, wait until some writing on flight finished, and only after that start reading. And here is the problem for that particular case. We write into different locations, into different addresses, but inside the same cache lines from different hyperthreads, and Intel's disambiguator fucked up. He can't do anything. But they help us. They did particular event which looked into that issue. We could collect that event with that name, and we could see that on the same core, hyperthreading. We have a lot of machine clears, memory ordering, but they don't happen in any other cases. And it's how to catch that situation for hyperthreading, and for honestly different cores, we have to fight for RFO. Request for ownership is a situation when one core send to other, cache of one core send request to cache of other core, give me these cache lines, I am going to write here. I want to write here, and just we could realize that these kind of events, there are different kind of events, drastically different in case of zero in parity and false shared case. Okay, I'll skip this stuff and just summary about high performance. You shouldn't realize that sometimes you don't need even know that you can't fight with that situation. You could achieve a high performance on other levels, more top levels, but if you have to, like people who is writing very concurrent, very fast performance application, and etc., you should know all of this here. You should know the whole full stack, but of course it's may create a problems of overflow for you. And just some kind of useful reading. Thank you, guys.